All right, well, welcome everybody. So today we're talking about, I think it's chapter 5, but the dimensions linear algebra chapter. So let me share my screen. And here's our outline for this chapter. And then not sure exactly how last week went, but basically, my plan is to just kind of go through the sections and pause with each one and see if people have any questions, any comments, any insight. There's a few places where, like I know that this math is really going to get used later on, but it's not like I've read ahead. I'm not an expert on quantum computing. So any other insight people have as to if there are concepts that, better make sure you understand this one. That's always going to be useful. All right, so chapter 5, the first section is just talking about the real number plane and complex numbers, and so we talk about coordinates, bases, the standard basis, and I think prior to reading this book, I always thought of complex number plane with sort of like the real numbers on the x-axis and the imaginary numbers on the y-axis as sort of like the way to think of complex numbers, as opposed to just sort of like, oh, well, this is sort of like a, I don't know, sort of an alternate way, but the complex numbers are sort of a one-dimensional object. They're not a two-dimensional object. It's just if you think of the two components as real numbers, then they're, so that's, I think, like one of the really key things to understand is that don't make the mistake that I did prior to this book, thinking that complex numbers are sort of two-dimensional. And then the idea of basis is like really important, and they use this terminology E for the standard basis, which we find very intuitive, right? Like just 1, 0, 0, 1, but that's like super duper important, and important to understand that that's not the only possible basis. And then later in the chapter, they even say that the bases don't need to be orthogonal. They just need to be linearly independent. But we're primarily, I think, going to use orthogonal bases when we do quantum computing. All right, that's me just adding a little bit. Anybody else have questions, comments?
I haven't gone deep enough on the linear algebra or the quantum stuff to see it yet, but I think it's just kind of an interesting idea that you might be able to change some basis and then all of a sudden some problem is much more easy than it originally was.
Mm-hmm. Yeah, we're going to get to that section. I used to live in the Bay Area, and I think about in San Francisco, you have this Market Street, this main street, and it's on a diagonal. It's like northeast to southwest, right? And everything above Market Street is on a north-south grid. So the roads run north, south, and east, west. Everything south of Market runs parallel to Market, so it's all at a 45-degree angle. So the example in the book, kind of like totally made sense to me that like if you're talking about walking south of Market, you really would want to use a basis that's northeast, southwest. But if you're walking north of Market, you just want to use the standard north, south, east, west. Because otherwise you're saying like walk on a diagonal line. That's confusing because you're just walking straight down the street.
Okay, I have a couple of comments. First, they have very intimidating quote at the beginning of the chapter, which claims that dealing with high dimensions is not so simple. And last time I already said that I'm a mathematician. I know that very many mathematicians, quite majority actually, cannot imagine how to work with high dimensions, cannot actually see any representation of them, well, besides 3 dimensions in their head. But they computed, all the computations are well known, you just manipulate with symbols and such and such. I personally knew 2 mathematicians who can imagine things in 4th dimension. And one of them was my ex-husband. I lived with him for 15 years. It didn't help. Okay, so this is about multidimensionality, and another thing which I would like to mention, complex space, multidimensional in particular, complex space, even two-dimensional, is rather different from real space. So if you know very well usual real vector space, and you think that you can glide through the chapter, then yes, you can glide through the stuff which is the same as real vector space, but on complex space, please pay attention. That's it.
Cool. Thank you. Thanks, Maya. All right. So if nothing else, then Maya just mentioned vector spaces. So so we're going to talk about vector spaces, linear algebra. So we have the formal requirements for vector space. And basically, you've got addition, you've got scalar multiplication. And then we formally defined linear dependence basis and standard basis. So again, we talked about these in section 1 informally, and now the author defined them generically and formally. So section 5.3 gets into linear maps. You know, I don't remember, it's been so many years, but I don't remember using the term linear maps when I took linear algebra. Maybe my class was a little bit more applied. I don't know. But so basically a linear function that we saw somewhere earlier in the book, right? Maps individual numbers to other individual numbers, and it has certain properties, right? The things that we think of linear. And so linear maps map vectors from one vector space into vectors in another vector space. And so from this, you can have the terms linear transformation, the identity, zero transformation is not particularly useful. You map everything to zero. Whether something's invertible, so whether you can go whether you can always go backwards if you went forwards. So any comments or question about linear maps? All right. So in terms of linear maps, when we send qubits through gates, I'm pretty sure we are going to be applying linear maps. So that's why this chapter really focuses on linear maps. And so you're going to have a vector in a certain vector space, and it will be transformed by this map. Map meaning basically just function. Let's see here. Algebraic structure. So I'm not sure. I don't know if anybody else knows. I think algebra is very useful. I don't know that all of this algebra will be absolutely required to understand quantum computing. Like if you know that something has like group structure, that's like very interesting, but we'll see. So invertible linear transformations form a non-commutative group under composition. And if you have a collection of linear transformations, this set of linear transformations, they themselves are a group under addition and a non-commutative ring, with composition being the second operation. Instead of typically, when you hear about rings, you think about multiplication being the second operation. Interesting, not sure that we need to know that stuff. So then we get into examples of linear transformations, and I think we're going to see certain ones of these a lot. So stretches, reflections, rotations, shears. These are all invertible, and these are all linear transformations. Projections sort of reduce dimensionality. So because you're losing information, they're not invertible, but they are linear maps, linear transformations. And you have injections, which are one-to-one. I saw this somewhere else, so I included this in the notes. This wasn't in the book, but if you just have a function that, say, maps the point AB to the point A plus 1B, okay, that is something you can very easily do with you know, it's an affine transformation. So like you might think of that as a linear transformation, right? It's just moving everything to the right one. But affine does not mean linear map. So even though it's a linear, it's a linear, I don't have the right math jargon, but it's a linear operation, but it is not a linear map. So don't confuse the idea that anything that involves only powers up to 1 is therefore a linear map. Okay. And the simplest way to be sure that this moving everything to the right one is not a linear map is that you always have to map the origin in one vector space to the origin in another vector space. All your like addition and multiplication is going to break if you don't map the origin. So this one clearly does not do that. It maps the origin to the point 1, 0. Any other comments or questions?
That's good to know. Thanks for bringing that up, because I would have missed that.
Yeah, it's sort of easy to just think like, oh, everything's linear. You know, like there are linear things you can do that are not maps. And so let me just jump ahead and say, so if you create a vector space to represent the state of some quantum particle or whatever, qubit, right? And you have the before state and you have the after state, then you are going to need a linear map because they're both vector spaces. You're going to need, you know, something that maps from one to the other. And so you can't have something that would map to something that's not a valid state for your particle. Now, I don't know exactly how we build gates that can do the transformations that we talk about, but nevertheless, it's easy to see that anything that breaks these rules absolutely is never going to have a real world equivalent because it's going to point to sort of a non-existent, you know, possibility. Okay, so we then get into matrix notations. So rows, columns, mentioned diagonal, transpose, symmetric matrices. Once we get into complex matrices, then instead of symmetric matrices, we're talking about Hermitian matrices. And we're going to see all the time this idea of the conjugate of a matrix as well as the adjoint, which is the conjugate transpose. Not sure if we need it for quantum computing, but boy, oh boy, do you see a lot of stuff in linear algebra in its use about positive definite, positive semi-definite matrices. So, you know, knowing that you have all positive real eigenvalues is just this shortcut that gets used in all sorts of things. So if you read ML papers, you're definitely going, some of the more theoreticals, you're definitely going to see places where people say, hey, I'm doing this thing, and at this point, I prove that this thing is positive definite. And therefore, there's certain shortcuts they can say because we know all these properties about them. Yeah, Maya?
Yes, about complex numbers and qubits in physics. The thing is that when you deal in very small dimensions and you go to string theory, then things that behave like the complex, the dimension they consider, you know, I don't know exactly. I didn't study the string theory itself. I was doing some work on structures which are used in string theory, and I've heard some physicians talking about it. So they have dimensions like 5 and 6, and they pretty much use complex numbers there, complex number fields. So yeah, I guess we'll see.
Yeah, I don't know if we'll ever know why, other than just it works. The math seems to line up if you use complex numbers, and it doesn't work if you try and move it to real numbers.
Yes, this is what they said. why you come up with this kind of idea. And they said, well, the computations use correct result, realistic results. So.
Yep. Okay. Any other comments or questions about our matrices, both ones with real numbers in the rows, all the, spots, rows, and columns, as well as complex numbers in the rows and columns? All right. So then 542, how do these matrices have to do with linear maps? So the author goes through and defines matrix multiplication. I think most people have probably seen matrix multiplication. And then makes the point of saying that vectors are always represented with respect to a particular basis. I think this is going to be important with quantum computing occasionally. And I've pretty much never really thought about things except in the standard basis, in 3 dimensions, 1, 0, 0, 0, 1, 0, 0, 0, 1, right? And certainly in linear algebra class, we talked about that you can have other bases that span the vector space. But perhaps it was just my failing. I just thought of it in terms of like, are they linearly independent? Do they span? I didn't ever actually think of them as being useful. But so I think that's the difference here, is that we will find, like Ryan was saying, that if sometimes you change bases and you think of things in terms of that. The other thing I think we'll see is that you guys have probably seen enough that that, like, hey, you can have a qubit and it's, let's say, 75% chance when you measure it, you're going to get a 1, and 25% chance, a 25% chance when you measure it, you're going to get a 0, right? You guys probably read enough literature to know that. You can actually measure it in a basis other than the standard basis, so if you have like a 45-degree angle basis or something like that, I don't know exactly how, but basically you can measure it in that basis instead of measuring it in the standard basis. And so whatever that equivalent is, it may no longer be 75-25, right? In that basis, maybe it's 85-15 or whatever. But like, so hold on to those those different bases. All right. What else was in here? So then the author shows examples of what would a matrix look like that if you left multiplied a vector by that matrix, it would do a stretch, it would do a reflection, it would do a rotation, it would do a shear. That was kind of helpful for me, especially to start with nice small ones that I can get my head around. I don't know about this book, but in other stuff I've peeked at for quantum computing, they just very glibly say, oh, and look, and this is a rotation about the x-axis, and oh, look, this is so like I was very thankful that he gave like nice simple examples of these. And then one thing, just in case you haven't run into this too much, but like when you have something like matrix multiplication, or it's like when you do functions on things like f of whatever, the thing that you're operating on is on the right. And so if you sort of look at the nesting of things like move outwards, right? So if I'm doing, f of g of h of x, then the h is the furthest to the right, the g is in the middle, and the f is on the far left. So you always perform these operations from right to left, which as an English language reader, we're reading left to right, So naturally, if you tell me 2 + 3 + 4 + 5, I'm going to add 2 and 3 first, and then 4, and then 5. But you have to be very careful when you have multiple matrix multiplication. If you have A times B times C times a vector x, you have to multiply C times x first, and then B times that product, and then A. Now, in certain cases, you get the same answer either direction, but just know that you always have to do these operations from right to left. All right, so that was That was this section. Any other questions, thoughts, comments?
Just a comment. The way to remember in which order we have composition of matrix is to remember that when you have a vector which is always on the right, at first you multiply matrix by this vector, and then you go to the next matrix which is to the left.
Right. Yep. Correct. Yes. You always do the closest thing first, and the vector's always on the right. So you're always left multiplying. All right. Matrix algebra. So arithmetic on matrices. Don't think we're going to do a lot of it, but I don't know. But you can add and subtract matrices that are the same size. You can do scalar multiplication. We've defined matrix multiplication. And if you didn't know this, so the transpose of A times B is the same thing as B transpose times A transpose, but you do have to flip the order. And then the same thing is true if you have complex numbers. So the adjoint of A times B is the multiplication of B adjoint times A adjoint. And if you know the way matrix multiplication works, you're sort of like taking one row, multiplying it by one column. So when you transpose them, then columns become rows, rows becomes columns. And so it's sort of like, you can see you're still multiplying the exact same items. It's just you've now sort of flipped everything around the diagonal when you do it that way. All right, let's see here. Arithmetic on square matrices. So now if you have actual square matrices, now we can talk about inverses and the determinants and the traces. I remember doing a lot of stuff with determinants. I actually don't remember discussing traces that much in my linear algebra class, but I've seen it in ML papers. So I think these are good concepts to know. So if the determinant's 0, then your matrix will not have an inverse. This also ties to things like what is the rank of your matrix. So if the columns don't, span the full thing, then you're going to have a 0 determinant, and you're going to not be able to invert that square matrix. Let's see here. In terms of the questions,
I'm still a little fuzzy on what the determinant is. Is there a geometric representation of it, or does somebody have a?
No, Maya, do you have anything?
Yes, determinant could be equivalent to the volume. And when we have a singular matrix, then this volume will be 0. Volume of some kind of, I forget how the structure is called, but it is generalization of, I don't remember how it is called in English, so sorry. It is a not quite rectangular, but say sheer rectangular, which is
Seems like it's kind of almost like an area or a volume, but can be negative, which normally a volume or an area
yes,
is not possible.
it means that orientation is involved, actually.
Yeah. So basically the if we consider like 2 dimensions, right? I mean, vector A and vector B, right? And then if you look at the area of the parallelogram, which
parallelogram. So thank you. Yeah.
Thank you. Yeah. So which actually comes with if you complete vector A, vector B, and take vector A, vector B, and just complete the parallelogram. Basically you draw a line which is parallel to vector A, the other side, and basically you can you make that parallelogram. So that's the determinant is this determinant of with would be the area spanned by that. I mean, actually, determinant also comes in the cross product, right? I mean, basically, in a vector cross product, you would actually A cross B, you write it as a determinant, and then that's another vector. The determinant, sorry, would be the actual the magnitude of the determinant would be the area spanned by those two vectors. And this can be extended to 3 dimensions, or like that will be the one ABC.
Thanks, guys. Yeah.
Thank you.
If you think about a single vector having a length, then a matrix would have an area or volume or hypervolume or whatever you want to call that, right? If I take a vector and I multiply each of the individual numbers in that vector by 2, you kind of have an intuition what happens to the length of that vector. It's going to grow by 2, right? If I had a 2 by 2 matrix and let's say it's representing a parallelogram, if you multiply each of the sides by 2, what would you expect to happen to the area of that parallelogram?
To be multiplied by 4.
4, yeah.
Right, it's not going to double, it's going to multiply by 4. And that is exactly the property that the determinant will also have. It will grow by 4 if you doubled each of the individual numbers in a matrix.
Okay.
If you have a 3 by 3 matrix, you double all the numbers, and the determinant will be a factor of 8 of what it used to be. So in that sense, you asked for like intuition, it really is kind of expressing area or volume of the numbers in that. And it helps with what they were saying, that if you think of a matrix not as a square, but as just a bunch of column vectors that are smushed next to each other, then you can say, what is the property of their sort of interrelation? And so then this area of the parallelogram is sort of that. Now, like why you have negatives and positives in there, I'm not exactly completely sure. But
well, if you swap 2 columns in the matrix, then determinant changes sign. So it is about orientation and what order you consider the vectors.
Okay. Yeah. I guess. Yeah. If you think about it hard enough, then the fact that you could like permute the columns or whatever, but you haven't fundamentally changed your matrix when you just permute things, right? It's kind of arbitrary. Basically, it's what basis if you just permute things, whatever, you know.
Yeah, it's almost like you have an area that's an absolute value, and then you have this determinant that is kind of the area, but in a direction which could be positive or negative.
Yeah. And in this case, it's just signed. So it's
you
know, like you can imagine what, I don't even know, but like first quadrant, third quadrant are positive and the other quadrants are negative, whatever. But the sign, I think, tends to be not that important for the determinant, but the absolute value of it tends to be very important.
Sign could be important too. Sometimes. Anyway, if you want to check it out, you can consider determinant of 2-dimensional matrix and to see that it is actually area of the corresponding parallelogram, because you can discover the inner product which is needed for cosine to compute the area of a parallelogram.
Can I share screen for a second, Ted?
Yes. Can you try, or do I need to pause for you?
It doesn't let me until you pause.
Oh, you know what? I think that's a security thing I did because of unfortunately Zoom bombers.
Okay, perfect. Everyone's kind of touched on these points already. You guys can see the YouTube screen, right? So this is I when I was trying to brush up on linear algebra, I watched a bunch of three blue, one brown. Basically the way they described it is you've got this unit square, and so with this, the determinant is telling you how the area is going to be affected. So like they can do this shear effect, and it's still a 1 by 1 technically, so it's got area of 1, so the determinant is still 1. But then you can do something like this, you're actually changing the magnitude on top of that shear, and then all of a sudden you have 6 times the area of whatever you had. And so there's a few more examples of this, like showing when it's 0, one of the dimensions gets crushed down and stuff like that. So if anyone wants further kind of visual look at this, I recommend this video.
You said it was 3 blue, 1 brown?
Yeah, I put a link to the whole series in the chat, so it's awesome. Video 6 out of that. Yeah.
And 3
cool.
blue, 1
so
brown
much.
has beautiful graphics, and covers a lot of great concepts. I don't think Ryan, he does more advanced things like back propagation, but like just math when it comes to stuff like determinants and other like core math things. Some really amazing stuff. I think I watched one of the ones on like Fourier transform or whatever. It was really cool.
Yeah.
All
His
right.
animations are very good.
Yeah. Isn't he the guy that basically created his own graphics library to do animation?
He built Manim and then has made all his animations with the library that he made.
Wow. Cool, thank you.
So one other comment to tie in things. So if this represents sort of like how big these vectors are and the area or volume, so then what if you took a vector X and you multiply it by this matrix, and then you multiplied it a whole bunch of times? What would you expect to happen to that vector, right? If the determinant is, say, large, like let's say it's 10, and you multiplied it by that 5 times, pretty much expect that the result of that multiplication is going to have a much larger length than the one you started with. In fact, maybe roughly like 100,000 times longer, because you keep multiplying by this thing with sort of area volume 10. And there's a similar principle that we haven't gotten to the section yet, but when you do the when you find the eigenvalues and eigenvectors of a matrix, then the eigenvalues explicitly encode sort of, imagine like the stretch factor in each of the principal components. Okay, so when you do, so like, this isn't necessarily how a mathematician would say, but since we in machine learning often do like PCA, and you know that breaks down to these orthogonal components, right? So if you do this PCA decomposition of this matrix, then the eigenvalues represent the stretch factor in each of those. And so you absolutely can take those eigenvalues, what they call the spectra of that matrix. And if those eigenvalues multiply to, say, 10, then it is absolutely the case that if you multiply like a non-zero vector by that matrix 5 times, you should expect it to grow by length by a factor of 100,000. And so I've seen ML papers where they say, if the spectra of your weight matrices is 10, and you've got lots of layers, you can fully expect that your values are going to overflow at some point, because you're just constantly multiplying by 10 by 10 by 10. And that's where you see things like layer norm, batch norm, or whatever, are trying to always squash things back between 0 and 1, because you know that if it's 10, you're just going to overflow at some point in your machine learning.
Also, an interesting point is that in a diagonal vector, which is basically when you do an eigenvalue decomposition, you're trying to get represent any matrix as a product of S U basically a Q and then a diagonal matrix with eigenvalues, which is say lambda, and then V, right? Basically, so Q and V are unitary matrices or matrices with this determinant is 1. These are kind of visualized as rotations. And then in the middle, you have this lambda matrix, which is a diagonal matrix of eigenvalues, right? So the lambda matrix basically encapsulates the whole determinant, because the determinant of a diagonal matrix is, as Ted pointed, like he's talking about eigenvalues describing the size, right? So like if lambda 0, lambda 1, lambda 2, etc., right? So you just put them all in diagonals on the diagonal. The determinant of that would be just the product of the eigenvalues, lambda 0 times lambda 1 times lambda 2, blah blah blah. So basically, the determinant of any matrix is equal to the product of its eigenvalues. So you can represent any matrix as a like these two unitary matrices. Unitary matrices are just matrices whose determinant is 1, and these are viewed as rotations in I think here in this book talks about rotations. So any rotation is described as a unitary matrix, and then you it's lambda, which is kind of like which says how the stretch is or whatever it is, and then so yeah. So when you that's another way of like the determinant of the entire matrix would be basically the product of its eigenvalues. Thanks.
Thank you.
Interesting.
All right. So we actually are going to cover some of these other topics in a moment. So let me move on, and then we can have more questions or discussions as they come. But thanks for asking that question, because I actually didn't know most of what everyone just shared about determinants, but I feel like I'm more comfortable with determinants now. Okay, so I haven't really been pausing on the questions, but there are a few questions that I thought were sort of interesting. So what is the determinant of a rotation matrix in R2? So they show that formula with like the sine and the cosines or whatever. I don't know if you guys looked at this question.
It should be 1 because distances are not changing.
We know the distance doesn't change with the rotation. And in fact, when you do it, you get sine squared plus cosine squared.
Yeah,
Yes.
that was my kind of instant take on that. Was that it probably is 1.
Yes.
Because you're ending up with that rotational identity.
Right. And so the eigenvalues, the determinant, it's 1 for a rotation matrix. And we are going to talk about these length preserving operations.
Oh, yeah, and it preserves orientation. Sorry for this. This is, if it would, swap orientation, it would be -1, but it preserves orientation. So it is just 1.
And then why is the trace of a Hermitian matrix real? So
that kind of related to the why the diagonal of a is it Hermitian or Hermatian?
I don't know. Do people say a soft sh or a hard t? Hermitian or Hermitian?
Hermatian. I don't know.
Usually,
Anyway.
I think they say I mean all the all the classes I've taken, they call it Hermitian.
Hermitian.
I wasn't sure if it's a soft, so I guess it's a soft Hermitian.
Hermitian. Okay. So if the diagonal of a Hermitian matrix is real because it has to be self-conjugating,
Yes.
Is that right? And so that would be why the trace would be real as well.
Exactly. So when you take the adjoint, it has to already be real. Yeah. Okay. Cartesian products, I'm not sure why the author included this. I think maybe, I don't know. I'm not sure how combining state spaces is going to relate or not relate to Cartesian products. But basically, you can just sort of like combine two vector spaces, sort of the gist. All right, so then we have a whole section on length and preserving it, and this is going to be because in nature we see that length is preserved in the quantum realm. So why all this stuff comes in. All right, so first section, we define the dot product, where you just coordinate-wise, you multiply the different numbers, and orthogonal vectors have a zero dot product. Then we get to the inner product, and this is something that I highlighted this for myself. I've never felt really comfortable. I use inner products in various things, whatever support vector machines, but I've never really had a good intuition, just like Kirk was kind enough to ask about like determinants. Like, I don't know if anybody can explain to me, like, other than just memorizing the properties of an inner product, is there any intuition around like what an inner product is and why it is what it is? I don't know.
It's a very convenient property for different vector spaces. You define inner product, you can define what is orthonormal, and it is not necessarily, physical angles. You can define vector space as functions, and then you need to know what means that if functions are orthonormal when you want to find the basis, for example. For example, it is important when we work with array of polynomial functions. What is orthonormal there? And orthonormality is actually important for probability theory. I don't know why they're going to use it. So, okay, orthonormality is important for probability theory because you need to compute how vectors are dependable on each other. And you want independent vectors. And you can find orthonormal polynomials. They are not just usual 1x, x squared, and x3. They're different. But you can find polynomials which are orthonormal and which are usually used for polynomial linear regression. By the way, in R, if you ever use it, then they use exactly orthonormal polynomials behind the scene. So I hope it was helpful. I'm not sure.
Yeah, great, Maya. Actually, just to extend that that thought process, right? So when we think of two lines, right, the angle theta between the lines, we kind of see the notion of that, right? So and then when the angle theta is for 90 degrees, that's when we call perpendicular or not. So the inner product, I mean, if you in a two-dimensional space, like modulo A times modulo B times cos theta, right? So basically, you could think of cos theta as the inner product divided by magnitude of A times magnitude of B, right? So it's just extending that notion, the angle between the two vectors, and if the inner product is 0, cos theta is 0, right? I mean, so in a product is 0, cos theta is 0, or theta is 90 degrees, or pi by 2. So that's an extension of that, and then also it is yeah, it tells you that like the two, like the when you talk about two choosing independent basis, I mean, you also want to try and get them normal so that you're actually, that's a natural basis for a vector space, right? So you want to see that they're perpendicular to each other, right? If possible. That's the so extending the notion of angle. I think this is where inner product comes in, and you have like also the famous cosine rule, right? In a triangle, you have A, B, and angle theta. Then the third side C is related to the two sides A and B by C squared equals A squared plus B squared minus 2A. Is it minus or plus? Yeah, plus 2ABC cos theta. Yeah, minus. I think it's minus because yeah. And in the case of theta being pi by 2, that the cos theta gets to 0, and then you have the Pythagoras theorem, right? So these notions kind of extend out to you know, multi-dimensional, etc. And essentially, it's yeah, there's something called Cauchy-Schwarz inequality, and the fact that cos theta modulus of cos theta is less than 1, and I think yeah, this extends to any vector space and even matrices and in general.
So from a probability aspect, could you say that that two vectors, if they're orthonormal, are not influencing each other either by having you know, moving in the same direction as each other, or by being of dissimilar magnitudes? So once they have the same magnitude and they are completely orthogonal, then they're completely, they don't influence each other. Is that, am I on the right track there?
Yeah, independent vectors, right? So basically independent where independent probability distributions would have like their inner product 0 kind of, yeah. Mm-hmm. I think that's
orthogonal vectors are independent in any case. You don't need even to scale them in any way, because inner product, well, if you scale it, it is just multiplication by a scalar. And if you already have 0, then scaling will give you 0 too.
So what's the advantage of having going from orthogonal to orthonormal?
Orthogonal means that just inner product equals 0. Orthonormal means that in addition, length of each vector, which we consider is 1.
And if the scaling doesn't matter, what's the use of that, or how does that?
Sorry, maybe I didn't hear well, but orthonormal vectors are all have length 0. So you cannot scale them. You can rotate them.
Mm-hmm.
But
all right, so I think maybe I'm gonna rein things in.
Okay.
So I know I asked this question, but maybe we can, if people want, they can
yeah, I might have to
talk further on Slack or
yeah.
whatever. Just so you know, Kirk, I don't know the linkage between this and probability, so I can't answer that question.
Can I make a quick comment?
Oh yeah, please go ahead, Mario.
Page 180 of the text. There's a formula for the dot product in terms of the norms of the vectors and times the cosine of the angle between the vectors. If the vectors represent data, essentially what they give you is the formula for correlation between the two vectors. So that way you can relate it to probability.
Yeah, I think Oh, okay.
Huh.
Okay. So the more collinear they are, the more correlated they are, the more orthogonal they are, the more independent
Right.
they are. Okay.
Okay.
Thank you.
Interesting. Thanks.
All right. So in this section 5.7, we're talking about length. So you've got dot products and inner products, and so now we're going to define the Euclidean norm. So this is just the square root of the inner product of a vector with itself. And so now that you've defined length, you can say that something is of length 1. And so you can define your unit vectors, and you can define, orthonormal basis, meaning that they're orthogonal and they're length 1. Let's see here. It talks about reflections. I think this is meant to just be an example. So, in this one thing, they have this reflection matrix, and if you multiply it by itself, you end up getting I, the two-dimensional identity. So A is its own inverse. Not sure if there's much there. Any comments before I move on? All right. So extending from real numbers now to complex numbers. And again, I can't really visualize a two-dimensional complex space. Wish I could. But so even for a small 2x2 matrix with complex numbers, I don't have a geometric picture in my head. But for unitary matrices, its adjoint is its inverse. And I actually like this section because basically the picture that I had, I never had this before reading this chapter, but basically when you multiply a matrix by its adjoint, what you're basically doing is you're creating the inner product of each column, each row, with itself. And since they're length 1, then basically you're always going to get sort of ones on the diagonal, and then you're going to get zeros everywhere else if you do the inner product of anything with any of the other orthogonal vectors. So to me, there's sort of this intuition of like why when you multiply something, because to me it was just this magical thing. Why would you multiply something by its adjoint? I don't know, but when you do it, you basically get, the product just is all the inner products of the different columns. And so if the original columns are all orthogonal, then basically you're going to get ones when you multiply with yourself, you're going to get zeros with everything else.
So just a corollary of that is that the columns or the rows of a unitary matrix form orthonormal bases. So they have all magnitude 1, and they're all perpendicular to each other.
Yeah, awesome. So your determinant is always absolute value 1, and your eigenvalues are 1. Like everything's just 1, 1, 1, 1, 1 all over the place with these things. And so we're going to see in our qubits where we have a vector of length 1, and it's always length 1 in terms of the state of this thing, then the only possible physical operations on it have to be unitary transformations, because in the real world, the length never changes from 1. So if I had something that I just say mathematically, well, this is a cool thing that I like this matrix, and it multiplies by 2, then you can just say, well, there will never be in the real world something that does that, because the state has to always have length 1. So that's why everything from here on out, it's going to be unitary. All the gates that we operate on qubits are all going to be unitary transformation. One other consequence of having unitary matrices is because the adjoint is its inverse, that means that unitary transformations are always invertible. And so that's one of the things that you see very early in quantum things, is that every operation you perform, every gate, everything is invertible. I don't know if any of you guys have studied physics. I don't know if like the concept of time running either forwards or backwards, if that invertibility just sort of is very intuitive then, because time doesn't physically, mathematically, time doesn't have a forward direction. It has whatever a relationship of this is on the left, this is on the right, but whether time is running forwards or running its backwards, I don't think mathematically makes any difference. So we think of ourselves as remembering the past, but what if actually time runs the opposite and we're remembering the future? I don't think you can disprove that that's the way the universe works. All right, any other comment on unitary matrices? Okay, systems of linear equations. I don't think we need to know about systems of linear equations, but I think that this, the stuff that was covered in here, helps with the next section, the change of basis. So basically, they show how you can write a system of linear equations as a matrix, square matrix, well, assuming it's the same number of equations as variables. Technically doesn't have to be square. But a matrix A with all of the coefficients times a vector x representing your variables or your whatever norm, you know, your basis, equals some constant b. And if the matrix A is invertible, there's a unique solution. Otherwise, you have possible that you wrote an equation that's impossible, or else you've got a subspace of solutions. So like 3 equations, 3 variables, you could have a single point, you could have a line, you could have a plane, or you could have infinite solutions. If you just say like 0 times a vector equals 0, then anything's a solution. But those will always be subspaces, whatever your solution is. Went into condition number, which is actually interesting in terms of if you're trying to write software to compute things. A high condition number means that since floating point numbers are imprecise, there's always some amount of rounding, that a high condition number, your small little rounding error could turn into a large error in your answer. I'm not sure why he included it. I don't know if that's going to come up somewhere in the quantum computing dealing with error correction or something. Change of basis. So in here, he basically says, if you have a different basis, I think he used the example of like the 45-degree angle basis. You can basically take the coordinates for the new basis written in our standard basis E, and you can line them up into a matrix. And then basically that is the matrix that will convert from that that basis into our standard basis E. And if you invert that matrix, then you can convert from E to that basis. I don't know. Anything else? Any questions or comments in terms of change of basis? I know we're going to do it. I don't know how important it is exactly for the quantum stuff later. All right.
The next chapter is eigenvalues and eigenvectors, and it is quite often involves change of base to eigenvectors from usual base.
Yeah. So okay, so basically the definition, right, of an eigenvector is that you multiply the matrix, left multiply matrix by that vector, and you'll get some multiple of that vector back out. And so basically, if you change basis to all the vector space with where all the eigenvectors are your new bases, then in fact you would wind up with your matrix as just being a diagonal matrix. I think somebody said that earlier. So when you do that singular value decomposition, you get your eigenvectors and you get your eigenvalues on the diagonal matrix, and that's basically, I think he said like the rotation. So that's basically just rotating your current thing into the new basis, such that the eigenvectors are your new basis vectors. And because it's a rotation, that's why those are determinant one, matrices. So I don't think we're going to get into it, but when you talk about eigenvalues, there's the characteristic polynomial. So you solve this determinant thing, and it's just going to be a bunch of multiplying and addition, and so you'll get a polynomial. It'll have the actual numbers from your matrix A, and it'll have this unknown lambda appears, and so you can find all the roots, and all the roots are your eigenvalues. And then he talked about diagonalizability, and so complex unitary matrices. We're going to be primarily working with unitary matrices for these quantum gates. They are always diagonalizable.
Okay, I would just like to note that if you remember PCA, which we all know and love, then technically what is done when you compute principal components is that you scale the matrix. Oh, sorry, not scale matrix. You scale the your features, and then you need to find eigenvalues, and this eigenvalues is actually the transformation which yields principal components.
Yep, cool. So I don't know. I don't think we're going to. I don't know. I haven't seen in any of the quantum stuff that I've peeked at. I haven't seen that much stuff on eigenvectors and eigenvalues, but we'll see. We'll see how much that comes up.
Eigenvalues come up a lot during difficult computations, and as you know, as with PCA, you could use it and you won't know it because it is in computations.
Yeah. All right, I can maybe share at the end, but there's this self-supervised learning paper called BYOL, Bring Your Own Latent, and it works, but people didn't, when they first created it, they didn't understand why it worked. And so there's been a bunch of analyses, and it turned out that they looked at the eigenvalues and they looked at the spectra, and it's the first time I ever saw something with like spectra and eigenvalues, and I was like, oh, that's really cool. Usually it was just like over my head, but basically they showed that there's this one part of the model that takes in the embedding of an image, and it multiplies it by these matrices, whatever, does this transformation, and it outputs essentially the identical original matrix that it got, but it does it in a non-trivial way. It's not just the identity matrix. It actually like has weird numbers, all over and everything. And so then they basically prove that you have to like have eigenvectors, and then you multiply it, and then you kind of get out the same thing in spectra, whatever. So it was cool. I was very pleased that instead of it just being like something that gave me a headache, it was actually something that I thought, oh, that's actually really cool. All right, so direct sums, there's this circle plus operator, and basically if you have a vector space of dimension n, a vector space of dimension m, you just sort of smush the coordinates together and you get a n plus m dimensional new vector space. Okay, so you can see how you would combine vector spaces. And the author mentions that in chapter 8, we're going to see the tensor product. And somebody here, keep me honest, I believe that when you do the tensor product of an n and an m dimensional vector space, then you're going to get an n times m dimensional new vector space, as opposed to an n plus m. Okay, so these are two ways you can sort of smush vector spaces together, and we are definitely going to use the n times m tensor product later on. I don't know if we're going to use this or if this is just sort of like a nice stepping stone before we get to the tensor product. Thanks for the thumbs up, Crystal. Okay, last section, we actually made it through. Homomorphisms. So I had to reread this section twice. I don't know about you guys. Again, mathematically interesting. Not sure exactly why the author included it, if it was because we need it or it's just because he thinks this is really cool. But TLDR, we've been talking about these linear maps, and linear maps between vector spaces are homomorphisms. They preserve addition and scalar multiplication. Cryptography. Okay. And so if you have a state space, a given vector space for some quantum information, and you apply some operation to it, a gate, let's call it, then the vector space, the output, it's going to be the same. It's still the same physical, qubits. So it has to be an operation that goes from vector space V back to vector space V. And so in fact, it's going to be this isomorphism from the state space of it to itself. So all the gates and other things that we look at are going to be linear maps. They're going to have unitary matrices, and they are also going to be these vector space homomorphisms, to use the technical term. Whew. Okay, final thing in the summary, author says, when we get to the qubit in just like 20 more pages, we're going to see that it is a small vector space, only two-dimensional, with complex numbers. So it's a 2D complex vector space. And so that's just one property. So like say the spin of electron can be represented by two-dimensional space of complex numbers. And then we'll learn other properties about how you measure it, how you whatever it. But when you combine different things like multiple electrons or multiple properties of an electron, then you're going to grow the number of spaces. Instead of 2D, it could be 4D, 6D, 8D, 10D, whatever. But that's why we need to talk about all this stuff, because we are going to represent our quantum bit of information. 2D vector space, we're going to need these unitary matrices in order to modify that data. But even after we modify it, it'll always still be a unit vector in this 2D complex space. And then we can bring multiple pieces of information together to get larger size vector spaces. I think that's the connection, all this linear algebra, why we have been pairing this in order to do the qubit stuff. All right, I actually thought we would not, this was a pretty long, dense chapter for me. Lots and lots of terminology, like crazy, left and right definitions, left and right. Any other questions about the content, questions about why we discuss this stuff, comments, anything?
I'm still kind of interested to see the application, because for me, I feel like I'm getting hit with a lot of definitions and properties and things, and I can understand the individual definitions. I don't understand what their application is eventually going to be.
Yeah, I'm experiencing the same thing. It's like, okay, how do we use this stuff? But I guess that's to come.
Yeah. So from what little I've seen, right, we're going to start with one qubit, and it's going to have a certain value V. and we're going to pass it through gates. We're going to modify it. So we're going to left multiply it by unitary matrices. That's one thing we're going to do. The other thing we're going to do is we're going to introduce more qubits. And so if you have 2 qubits, and you, again, I don't know how you build these, but if you have a special gate, it can take as inputs both the value of qubit 1 and the value of qubit 2, and it can do something to them. So you're going to then have a 4x4 matrix that expresses, unitary matrix that expresses what that gate is going to do to each of the qubits. Okay. So just in terms of like pure math, we're going to have the more qubits you have, if they all are inputs into a gate, I don't even know if we have gates that have more than 2 inputs at a time, but theoretically, if you do, then you can have bigger and bigger matrices that represent. And so the key thing that we haven't talked about yet, that's actually not going to be in chapter 7, the first qubit chapter, but the chapter after that, right? The first chapter is called 1 qubit, and then the next chapter is like 2, 3 more qubits. So then you have to talk about how do you represent the state space when you have multiple things? And that's where things get interesting, because it's not as simple as you would think in the non-quantum world. Don't know if that helps, but seems to be where we're headed. Other thoughts, questions?
So we are not cover probability today. Just I thought, okay, that maybe
No.
we will go through 2 chapters like it was last time.
Oh, no, this was such a long chapter that I didn't
Okay.
plan to do 2 this week, but I do think next week will be very light. Yeah, so the outline, I wouldn't call it notes, but the outline that I'm sharing on my screen is well, I'm glad abstract algebra is somebody's jam because it's not mine. So hopefully you can help us through all this stuff. Yeah, but so to the extent that it's helpful, I will on GitHub, I will add links to the outlines, and to the extent that like last week we had a breakdown, we didn't get a recording, but we'll post the recordings that we have up to YouTube. Give Ryan a little bit of time to get those uploaded. I'm trying to think anything else. All right, any other comments?
Yeah, would you say there's a lot of tie-in between quantum computing and just general machine learning?
I would say not yet. It's so new that I don't feel like we understand the tie-ins. But specifically, what we're going to see is that with qubits, we're going to be able to have this superposition. So if you have 8 standard classical bits, you can represent up to 256 different values, one at a time. Okay, so with 8 bits, I can represent one number and can have 256 values. But with 8 qubits, I can hold in them simultaneously 256 different values all at once. And if I do a certain operation on those 8 qubits, ideally, if I can build the right kind of computer, I can calculate, let's say I want to multiply them by 2, just as a super simple thing, silly example. I can, in one time step, I can multiply all 256 of them by 2 at the same time. And so you can get tremendous speed up. So you imagine that if you have enough qubits, if you have 10 qubits, then you have 2 to the 10th different values. If I have 50 qubits, I have 2 to the 50 different values. So if I'm trying to calculate something about, like, say, a molecule, and I have all these different things, it would be really nice to do this ridiculously exponential number of calculations in one time step, as opposed to a standard classical computer would have to do them all one at a time, and it would be exponential amount of time to do, 2 to the n number of multiplications, for example. So there are certain algorithms that can take advantage of this, but what it requires is that you have to somehow figure out how to represent your data and shove it all into these qubits and then do the operations on all of them at once. Okay, and then you have to figure out how to read out the information, because it turns out that that's tricky with quantum computers. So I think it's interesting. I think that we're going to see new algorithms and new things, and certain problems someone's going to come up with a way of solving it a lot faster. And who knows, maybe that will really help with drug discovery, because we can do calculations on molecules and things like that, or protein folding or something, But it is absolutely not the case that quantum computers are just going to utterly replace regular computers. It's not the case that anything in the world will suddenly become computable in polynomial time. They've already proved that they have new encryption algorithms that will not be able to be solved faster than exponential time on a quantum computer. And so today, if we're using blah-de-blah encryption, if we just switch to XYZ encryption, then it doesn't matter even if secretly somebody has a giant quantum computer that they've built and they just haven't told us. They're not going to be able to crack that except by brute force going through millions of years of calculations to try and guess your password.
Well,
that's my limited answer. Yes, please go ahead.
It can decrease the time which need for computations in a few times, but no, the change is not exponential. So if there was something which you can do, like on which you have several hours, then it could be cut in a few times. But if it would take like several years, then, well, it's not much of a help.
So my oversimplification is that if people figure out how to build quantum computers cheaply and easily, then basically the way right now, you might say, I want a computer with a GPU, and it's going to do certain things like matrix multiplication a lot faster than my regular, Intel chip. You can say, hey, I want a computer with a quantum QPU, because it's going to do certain calculations a lot faster than my regular thing. But your regular computer is still going to be doing, 90% of all the things you do. It's just right now, if you have a special thing, then you load up the stuff into the memory on your GPU, and you do a whole bunch of floating point calculations, and then you copy back the results to your normal memory, and you keep going on with life. So I think it'll be the same way, where it's like, oh, I happen to want to do this very complex thing. I'm going to offload it onto my QPU, and it's going to calculate that faster. And then I'm going to go on with my merry life. And everything like Microsoft Word is still going to work exactly the way it does right now.
Interesting.
Yeah, that's my guess. But for fair warning, I'm a terrible predictor of the future. When the World Wide Web came out, this was before we had search engines. So there's no Yahoo, no Google, whatever. I was like, this web stuff's stupid. It's not very helpful. I didn't sort of foresee search engines, which, make a big difference. So you can actually
Sure, very few people did.
Well, thanks for saying that, because I feel kind of like, well, I kind of feel dumb for saying that this web thing's really not that big a deal. All right, cool. So we've reached the bottom of the hour. So at 1:30, we normally transition. We have our just sort of open office hours where we discuss programming questions, machine learning questions, problem formulation, career questions, whatnot. So thanks everyone for joining us. We'll wrap up the quantum computing book club session here next week. Probability, again, probably short chapter. The week after that, we really roll up our sleeves, and finally we'll start talking about quantum information